Welcome, everyone. Thank you for joining us for today's ACIESP webinar. My name is Adriano Andricopulo. I'm Executive Director of ACIESP, and I will moderate this webinar and panel discussion. I want to thank the State of São Paulo Research Foundation, FAPESP, for the support in this webinar. A special thanks to Professor Luiz Melo, Marcelo Melletti, Roberta, and Felipe. At this time, the participants are ready to start. And I want to welcome our special guest today, Professor Yonath, who won the Nobel Prize in Chemistry 2009 for her studies of the structure and function of the ribosome. Also joining us today are Professors Vanderlan Bolzani, Paulo Artacho, and Regina Marcos. The webinar includes a presentation by Professor Yonath, followed by panel discussions and questions and answers sessions. After Ada's presentation, the audience will have the opportunity to ask questions. So please, send your questions at any time during the presentation via the YouTube chat, and I promise to keep a close eye on the chat window. And now, without further ado, I'm pleased to invite the President of the São Paulo State Academy of Sciences, Professor Vanderlan Bolzani, to introduce our speaker today. Please, Vanderlan, go ahead.
Good morning, distinguished Professor Yonath, current Director of the Helen Milton Kilmerman Center of Biomolecular Structure and Assembly of Weizmann Institute of Science in Rio, and Nobel Prize in Chemistry for her pioneering work on the structure of ribosomes. I am delighted you accepted our invitation to open ACIESP webinar series. Good morning, ladies and gentlemen, colleagues and friends. I am extremely glad to introduce this series of webinars as part of the work of new ACIESP directors elected recently. My colleagues, Paulo Artacho as Vice President and Adriano Andricopulo as Executive Director. Today, in our first ACIESP webinars, it is an enormous privilege to present all you watch us an account with Yonath, Nobel laureate scientist, and a woman with a brilliant head of curly hair. It is a truly an amazing history, and we're looking forward to hearing what she has to say today. We are inviting here outstanding international and national scientists for debate the latest advances of the state-of-the-art science aimed at solutions for a better quality of life for humanity today and future generations. In fact, we had decided to start a ACIESP Advanced School similar to those supported by FAPESP from São Paulo School of Advanced Science, which already had tradition in São Paulo with expenses granted by FAPESP. This would be developed based on the Nobel Advanced School we organized in 2011 to celebrate the International Year of Chemistry. The school organized in August 2011 in Campinas. We had 5 laureates in chemistry and was a fantastic and memorable school with the presence of Professor Yonath. I will speak in just a few minutes, who gave a wonderful and memorable talk entitled The Amazing Ribosomes. Those recognized at that moment, Professor Martin Schaufer from Columbia University, Nobel Prize in 2008, for discovery of development of green fluorescent proteins, Richard Roque from Massachusetts Institute of Technology, a Nobel Prize in 2005 for development metastatic organ synthesis, Professor Kurt Wurtisch from ATH Zurich, for the Script Research Institute, for Nobel Prize in 2003 for developing nuclear magnetic resonance method dedicated to biological macromolecules, and Ishi Nigishi, Purdue University, 2010, to develop a metal-based reaction called palladium cross-coupling to assay efficient synthesis of complex molecule. Thus, our São Paulo Nobel School is scheduled to take place in October 2020 with 4 confirmed Nobel Prize and 1 confirmed who inspired our 2011 school. Is a dream of mine, a dream to have in São Paulo an advanced school each 2 years dedicated to young talents. It would be a school where students and young research from all Latin America could interact with Nobel laureate. It would be an initiative inspired in the traditional Lindau laureate meeting, which started in 1951. Few Latin Americans and Brazilians have the opportunity to participate in the traditional and fantastic Lindau. Thus, the creation of a Nobel School here, something is a dream, and it would be incredible opportunity for talent from South America continent. Due to the world catastrophe that has befallen, it was necessary to cancel a planned Nobel School in October 2020. In response, I invited Nobel winners to participate in a series of ACIESP webinars, and naturally, the idea was enthusiastically embraced by my colleagues and friends Paulo and Adriano. And so it is a great pleasure that we begin this webinar series with Professor Ada Yonath, who enjoyed the idea and accepted to be the first speaker of this webinar. Professor Ada shared the Nobel Prize with Professor Venkatraman Ramachandran, current president of the Royal Society, and Thomas Zait from Yale University. His studies on the structure and function of ribosomes made her first Israeli woman to win a Nobel Prize out of 10 Israeli Nobel laureates, the first woman from Middle East to win a Nobel Prize in Science until 1917. She was the woman in 45 years to win Nobel Prize in Chemistry. Only in 2008, Frances Arnold from Caltech was awarded with his studies on direct evolution of enzyme. Our distinguished laureate Ada Yonath needs no formal presentation. However, I will add some details of your beautiful personal and academic life, as it's a great inspiration for our young women and young scientists, so full of talent and hopeful being great scientists in the future. Her parents, despite difficulty or humble circumstances, gave a very good formal education to Ada. They supported the Adora evidence, curiosity, and with the help and encouraging kindergarten teacher, has sent to a prestigious grammar school. Her parents loved outlining the kids' past, and with Ada, the history was much the same. At the age of 5, Yonath undertook ambitious effort to measure the height of her family's balcony using 2 tables, a chair of stool. The experiment was suspended when she fell down and broke the arm. The family moved to Tel Aviv in a year later to be close to her mother's family, where Yonath taught other students math and chemistry, and even cleaned to the chemistry lab and changed the tuition. In the 1970s, Yonath decided to study and focus on the mysteries of living cells and protein biosynthesis. She began with ribosomes, where protein synthesis occur, a puzzle to scientists because they had yet to determine ribosomes' molecular structure. However, given its size, lack of internal symmetry and stability, the ribosome was considered impossible to crystallize, and Professor Ada Yonath was considered a dream or a fool of trying. It took 20,000 attempts until the revelation came that ribosome from organism that lives under harsh conditions would be radiated during crystallization. In the early 80s, Yonath finally managed to crystallize a desert bacteria known the Geobacillum aterothermophilus. Ada Yonath, ever since she was a girl, has set herself seemingly impossible goals and then figured out how to reach them step by step. As a young scientist, she took on a challenge that others consider hopeless, mapping the structure of the ribosomes and preserve it for decades until she succeeded. Her determination and ingenuity allowed research to see and understand the complex and crucial molecule. And since the ribosome is a major bacterial target for antibiotics, her work has led to new antibiotics and better understanding of antibiotic resistance. Until today, she's remained at the Weizmann Institute and continues to work on demonstrate how more than 20 antibiotic function paving the way for new products to be developed based on ribosome structure. More recently, she has focused her effort in issues antibiotic resistance. She also wants to uncover the very beginnings of life itself, how ribosomes first became into being, they start create proteins. It sounds, but for other ambitions, but for Ada Yonath, discovering the origin of life is just the next step of a series of summits. It was a true privilege to celebrate together with her our recognition as distinguished women in science at the 43rd UPAC conference in San Juan, Puerto Rico in 2011 as part of the celebration of the International Week of Chemistry and her plenary conference at the 46th World Chemistry Congress of the International of the UPAC in 2017 in São Paulo. It was a memorable time we were together. The first time that the Congress had been held in Latin America in more than 10 years, and due to the excellent work of Professor Adriano Andricopulo at that time as president. To bring to the Congress to Brazil was an honor, and also to introduce her plenary letter with the most beautiful conference I have watched at that moment with Professor Ada. To all of those watching here, it is a great privilege and an honor to introduce Professor Ada Yonath. Professor Ada Yonath, the audience now is all of yours. Thank you so much to come here, and also thanks to FAPESP for support.
Shall I start now?
Yes,
Yeah.
Professor, please.
Yes, please.
Okay. So first I want to tell you that I'm very excited to speak in Brazil, which is known now around the whole world as one of the worst attacked countries by the coronavirus. And I'm so happy to see all of you healthy and ready to listen. I think that since I have only limited time, I will start directly with what I want to tell you. And what I want to tell you is my opinion about basic and basic science and oh God, wait a second. I see nothing. Okay. Basic science and the fact that, do you hear me? Do you hear me?
Yes,
Yes,
Professor.
yes, Professor.
Okay. So the fact that now most of the scientific world, not all, but most, are looking for fast applicativity. Fast, something that can be sold or made instead of, at least it's now by many, is treated as better and more important than basic science. In my opinion, basic science is the way to go to applicativity, and I will tell you now about my trip from basic science. This is what I wanted to do. I found myself doing also modern medicine. So I think that if I wanted to go directly to medicine, to make applications in medicine, I would be stopped much earlier, get only what I wanted, the product, and not open a new way like what happened to me. So first, for those of you that forgot what proteins are or know what proteins are, but not all the tasks, I'm showing here only a few tasks of proteins in human. Actually, proteins perform almost all cellular function in every cell, in bacteria, in elephants, whatever. So you can see here proteins that are structural proteins, sensory proteins, regulating proteins like insulin, transport proteins like hemoglobin, and enzymes that are cutting the food that we have, the proteins that we eat, in order to make from their components the proteins that we need. Because when we eat an egg, we are not eating it to get a chicken in our stomach, but in order to have a pool of proteins components, which are called amino acids, in order to make the proteins that we need. So one important concept in nature, in all nature, is that structure means function, or function means structure. And I'm using here a very simple way to show it. Here are paper clips, exactly the same paper clips after their structure was a little bit changed, even by fingers. They are exactly the same materials that are here. They were not heat, they were not frozen, they were not cut, just the structure was changed, and then the function is lost. And this is correct also for proteins. So what are proteins? All the cellular proteins are long chains, and they are made of their components, amino acids. And the fold of each protein, which is carefully designed for fulfilling its function, is determined by the sequence of the components of the amino acids that are building it in order to get the right structure. And the sequence of the building blocks of the amino acids, which enables the function, is dictated by the sequence of the genes that code for proteins. So I think that now everybody knows DNA and everybody knows what are genes. So I don't have to explain much, but I still want to remind you that DNA is a string of instructions.
Excuse me, Professor.
Yeah.
Would you like to share your screen, please?
What I want to share?
You have to share your screen, your presentation, please.
Didn't you see it? Until now, didn't you see the presentation?
No, not yet. You have to share.
I did share. Probably didn't.
Please, yes, try again, please.
So
yeah.
Now
please.
It works?
Yes, put it
yes,
in full mode, please.
I want to tell you that for me, Brazil was always the country of miracles.
Okay, thank you.
I love Brazil. I was in Brazil even as a tourist, even not as a scientist. And they are brilliant. So I go to the beginning. Now you see? Hello.
Perfect.
Yes, perfect, Professor.
Thank you. So we go from basic science. Now basic science is not highly regarded between the scientists and also between those that give the possibilities to do science. But in my opinion, this is the way to get real important inputs, even applicativity. To go directly to application is sometimes works, sometimes doesn't. But even if it works, this is very limited, just this application. And I want to show how we got to modern medicine from basic science. So first, you all know that proteins are performing almost all cellular functions. And here you can see some proteins that are typical to human, like transport proteins, hemoglobin, sensory proteins, structural proteins, and regulating proteins like insulin. And also there are enzymes. Enzymes are using the proteins that we eat, like eggs, meat, also the proteins from vegetables, in order to make the proteins that we need, because we eat every day. I ask children, why do you eat? Because mommy said that it's good. So it's much more than this. It's in order to build what we need, because proteins don't stay long in our body, except for skin and bones and things like that. Most of the proteins are being replaced after a few weeks, maximum a few months, in order to save their correct structure and get the correct function. Because in nature, structure means function, and function means structure. And you can see here paper clips. Here, this and this are the same like this and this after I change their structure. only structure. I didn't cut, I didn't hit, I didn't cool. Just with my fingers, I changed the structure, and these are already not functional. So function is structure and structure is function. So all cell proteins are long chains made of amino acids. These are the building blocks. And each protein has a fold. The fold of each protein, which is carefully designed for fulfilling its function, is determined by the sequence of the amino acids, just the sequence. And what determines the sequence? The sequence is determined by the gene. So each protein has a gene that is instructions how to build it. DNA has many genes, has other things too, but many genes. For each protein is a gene. The whole DNA language is made of 4 letters. 4 letters is the whole biology of the whole world. All the living creatures, all the flowers, all the trees, all the fish, everything is dictated by only 4 letters, 4 letters. And the sequence of the building blocks is determined by the building blocks of the proteins. So what really happens? There is DNA. The letters here are the 4 letters. So you can see base pairs. Each letter is called base. And you can see here only 4 colors. So here they are. Each 3 of them is dictating the insertion of 1 amino acid. So this is this one, and then afterwards this one and this. Each amino acid has a code of 3 letters. But here, all the information is covered by the structure. So it has to be, first of all, transcribed to a simpler molecule called RNA that is also made of a nucleic acid and letters, almost the same. One of them is really a little bit different, but the other 3 are the same. And this can be translated by ribosomes to proteins. So each 3 of them is getting in 1 amino acid. So in the cell, the ribosomes work all the time because always there is a protein to make, almost all the time. I don't want to say exactly all, but most of the time. And they can form 40 bonds between the amino acids. They are called peptide bonds in 1 second and hardly make mistakes. But the mistake is 1 to 500,000 or 1 to 1 million. So here I can tell you something personal about myself. I was the fastest student in the university when I studied chemistry because I was very poor and I had many jobs. So I needed to go to my jobs. So I had to finish the lab very quickly. And we had to make 1 peptide bond, 1, and I was the fastest. It took me 6 hours, and they can form 40 in 1 second. So they are really fantastic, the ribosomes. So there is a huge number of them that are functioning in every living cell. In mammalian cells, some cells may contain even millions of them, like in the liver, 4 to 6 million. Even bacterial cells contain up to 100,000 ribosomes. So now that we know how the ribosomes work, we describe them as factories that have 2 floors. You see the top floor and the lower floor. The instructions, it means the gene, or the translation of the gene is coming in like messenger RNA. And when there is here a triplet that is coding for this amino acid, for instance, it will go in and be connected to the growing protein. This happens inside. I don't know to draw inside. So this happens inside and in the lower floor. Then after this truck is coming in, it's a factory, so the trucks are bringing the building blocks. After the truck comes in, and the truck is actually also a nucleic acid called transfer RNA or tRNA. After they're coming in, this will be connected and the truck will go out with the other trucks. Then the message will move by a triplet for the next amino acid, and all needs a little bit of energy. Really, it's very efficient process. That's all what the ribosome does. It reads the instructions and make the bonds. So I want to tell you that all of it was known when I started. It was known that there are amino acids and trucks that take the tRNA, and the instructions come with DNA, and the ribosome is doing the reading and the binding. But it was not known how, and this is what was interesting for me. So what are ribosomes? Actually, the two floors of the factory are describing the two subunits of the ribosomes. There are two subunits that are sitting in the cell separate. Each of them is independent, and they come together, they associate in order to make a particle, a ribosome, that makes the protein. Within the ribosome, the small subunit is doing the decoding of the code, and the large subunit makes the bonds. So actually, this is a ribosome, small subunit, large subunit. Here, the tRNA that have the code and the amino acid. The decoding is here. The amino acid connection is here. So this is decoding, and this is the making the bond in the peptide bond between the two amino acids, and this happens in a feature that is called PTC, peptidyl transferase center, which is the position where the bonds are being made, and I'll talk about it later. And as I said earlier, the decoding is made here by a position that is called the decoding center. So it took 20 years to get the structures in order to understand the function. Within 3 or 4 months, we understood the function and we made a movie, a video. So you can see here the video. The messenger is coming to the small subunit, which takes it. You can see here, and it's now in place, and it is all directed and monitored by a factor which is called initiation factor. So in bacteria, there are 3 of them, and you can see here number 3. In human, there are many more. Now where everything is okay, the first track, the first tRNA can come with another initiation factor, number 2. And when everything is in place, the 2 factors went away, and the large subunit can come close and make the whole ribosome. Now everything is fine, and you see the active ribosome from the solution. You see here many amino acids are brought by elongation factors. The ribosome takes them in, out 40 times a second. And we took away the large subunit, or we'll take it away in a minute. You can see here how the decoding happens in the small subunit, and here down how the peptide bond is being made. And we left from the large subunit only the tunnel for which the new protein can go. So now you can see the whole ribosome again. The tunnel is inside the large subunit. And from the lower part, the protein comes out and folds to its right structure. And this happens alone or with chaperones. And the whole process continues until there is a stop codon, and then there is a termination factor that comes in, and it releases the two subunits. It releases the protein from the 2 subunits. It separates the 2 subunits. You can see the protein here, this blue thing down, and the whole system is waiting for the next tube. So simple, so beautiful. So, sorry. Just to show you that in the movie, everything was fuzzy, but actually we know the position of each and every atom, 4,500 atoms. Most of the ribosome is made of ribosomal RNA, the gray, And there are many proteins. In bacteria, about 55, in human, about 86, and 76. And each protein is shown in another color. So the small subunit is doing the decoding, and the large makes the peptide bond. So because of the fundamental role played by ribosomes, many antibiotics target them. So if one bacteria wants to get rid of another bacteria, it makes bullets against them. And these are antibiotics, but some of them are used also by medicine in order to get rid of bad bacteria, which are called pathogenic. So almost half, over 40% of the clinically useful antibiotics target protein biosynthesis, mostly by paralyzing ribosome. And that's very clever. You want to get rid of a bacteria, stop its possibility to make protein, so it will die next generation or the generation after. And generation in bacteria is a few hours, 4 hours, 6 hours, sometimes half a day. So the natural antibiotics, as I said earlier, are the weapons that bacteria from one type use for interfering with the cell life of different species. So the question that we asked is, how do the tiny antibiotic paralyze the giant ribosome? So I want to tell you, again, a personal comment. When I started, I wanted to understand how ribosomes work, and I didn't expect to get the structure, or at least, sorry, not that I didn't, I really wanted, but I had very, very many doubts that I will be able to do it because many others could not. But at that time, to see how antibiotics work, antibiotics that have molecular weight less than 1,000, stop 2.5 million, I didn't expect seeing it. And this is my bonus. I see all of them, and we understand how they function and how resistant. I'll show you. So first of all useful antibiotics, clinically useful antibiotics, the target ribosome, are binding to its functional site. So you can see every circle showing a family of antibiotics, small subunit on the right, large subunit on the left, and you can see that most of them bind to the decoding, or to the hinging dismotions, or to where the bond is being made, or to the tunnel. So once we understood it, and this was also relatively fast, only 2 or 3 years, I think, we made together with the 2 students that we made the first movie, we made also this one. So why doesn't it work? It worked a minute ago. So these 2 students of the Art Academy, they were really, wow. It's my best movie.
Professor Ada, there is a video button on the bottom of your screen. Maybe you can start your video from there.
Well, usually
you see
I start
a circle around the button here on the bottom. On the left side, the 4th button.
on the left side is a mute, and then video is open.
Okay. Maybe now.
No, it worked a minute ago. Wait a second. Okay, now it will work. So you can see here I'll show 4 antibiotics. Each of them represents a family. So what the factor is, the companies, the pharma companies did when the antibiotics came into use, they used the chemistry of nature of bacteria against bacteria and improved it to have it faster, less poisonous. Oh, here it is. So let's have a look. This is a small antibiotic called Edein. And look how clever, so small, so clever. Just doesn't let the messenger come in, the instructions. You see how clever? It was discovered in Poland. The second one is even smaller. It's called tetracycline, and it occupies the position of the tRNA that brings the amino acid. Look how small and how clever. That's it. Tetracycline is a very useful one. And probably you know about it. Maybe in Brazil it has another name. Now the third one is erythromycin. It's the first antibiotic after penicillin that came into use. And it's in the tunnel. And you can see only very short protein can be made. That's it. And the last one, from the point of view of chemistry, it's the cleverest. It goes into the bond. Oh, look, that's it, just in the bond. So as I told you, I didn't expect, but now we know. And now we also know how the problem of resistance happens. So it's one of the most severe problems in modern medicine. I think we all talk about coronavirus now, but I'll show you that antibiotics, resistance to antibiotics is even more troubling. So first of all, not far from you in Venezuela, there was a delegation that went to see how antibiotic resistance genes are, and they found out that when they found a tribe that never had any medicine, any European or American medicine, still they had antibiotic resistant genes, which means that it's really bacteria against bacteria. They are profit from accidental mutations or develop specific molecular pathways. I won't talk about all this, just to tell you. But the increasing appearance of multi-drug resistant strains of several pathogenic bacteria, together with the minimal, actually negligible number of new antibiotic drugs that are presently undergoing development in pharma factories, is a global problem. I give you some numbers. In USA, 2 million people fall ill each year from infectious diseases. In Europe, between 2010 and 2014, this is when the statistic was made, resistance caused 33,000 deaths yearly. And this happened in Europe when 1.6 billion euros was given to healthcare, and even when the consumption was twice as much as before. So the numbers are, for me, are really frightening. I don't have a real number, but I have an estimation. People that die from when they have long bad diseases like cancer. So sometimes a third of them, I don't want to say something, a third of them die when they are hospitalized in hospitals and catch an infection. So actually they die because of resistance to antibiotics. Although they have cancer, they could have lived longer. So third of the cancer patients. So it seems that we will soon revert back to the pre-antibiotic era, during which diseases caused by parasites or by simple or severe infections like pneumonia and so on were almost untreatable. Or as a World Health Organization say, we are reaching a post-antibiotic era. So consequently, the World Bank in 2014, that bank predicted and estimated that 3.8% of the global economy will be lost by 2050 just because of resistance. That's the World Bank. Yet, as I said earlier, very, very few new antibiotics are in development by the companies. Most large drug companies have stopped attempts of creating new antibiotics because of the huge mismatch, because the social value, it means our life, and the expenses that they need, and the fact that they need investors to invest. So you can see here, this is the increase on the left, the increase of drug resistance of 3 different antibiotics that have resistance. And the table shows between 1990 to 2002. And this is the amount of this is the amount of new antibiotics between 1980 and 2007 and 2014. Isn't it awful? So few. So actually, as I said earlier, for the chemist, they usually improve what is already given by nature. So this is a family called macrolide, that is a family's daughters and so on of erythromycin. You can see the structure here, and they made all types of changes. I won't go into the chemistry. But this is, I don't want to say easy, but it's doable. Looking for new antibiotics, something completely different, is hardly done in the world. So we can ask, can we combat resistance to antibiotics? So even I think that it's unlikely, because bacteria are clever and they want to live. And because this wish is cleverer than us, at least in terms of survival. But we can still do some things that maybe will not stop resistance, but minimize resistance. So in my lab, we are trying to make some contributions toward controlling or combating antibiotics resistance. So we determine the structures of the ribosomes from pathogenic disease-causing bacteria and compare them to ribosomes from harmless, from normal bacteria. And we got lots of lessons. The general one is that all bacterial ribosomes are similar. This is a general lesson, but there are detailed lessons, and I won't show you all of them. Let's talk about 4, lesson number 4. This is beyond my expectations. It's a lesson that allows us to suggest novel antibiotics, novel binding sites for antibiotics. So have a look here. You can see the skeleton of harmless bacteria, non-pathogenic, the gray, and these little pieces here and here and here, which are addition in the pathogenic. It's less than 8% of the whole structure, and everybody told me it's not important. But they have structures and they are on the surface. Like here, you can see here, this is the pathogenic on top of the non-pathogenic. Here they are the same. And this is a piece that is a addition. And in our idea, it can be a possible binding site. So in a model system, we identify 25 like this, new potential binding site. We block them one by one, and 16 of them, when we blocked, inhibit protein biosynthesis. So these are far from all active sites, and no antibiotic is known, and therefore we can think about making antibiotics. So what do we suggest? First of all, let's look at lesson number 6. Most of the ribosomal antibiotics are extensions of cores, like here, down here that you can see, which are not digestible, but also not biodegradable. So when a person gets antibiotic, even not overdose, or an animal gets it, these pieces are being are not digested, so they are being expelled of the body, and they may contaminate the environment because they are so small that the systems that are filtering the sewage don't catch them, and then they may get in, penetrate into the irrigation system and come back to us and increase resistance. Lesson number 7 is saving the microbiome. So now you all know that there are good bacteria in us that are called microbiome. These are millions, trillions of them. And the normal antibiotics, if they can penetrate the positions of the microbiome, like the guts, ears, lung, and skin, they can if they can get there, they can destroy them. So they can destroy the flora of our good life. So so we can make antibiotics that do not destroy the good one, the flora, the microbiome. So let's go back to the main point, how I started. Owing to vital role played by the ribosomes, there are 40% of clinical antibiotics that destroy them, but also, which I didn't show, and I won't talk much, just show you one slide, cells developed a specific method for preservation, cells of bacteria. So have a look here. This happens when there is a problem, when there are extreme conditions. So the microorganism survival under extreme condition is making dimers of them. You see here one, and the second, or from the other side from here. And these dimers are blocking each other from work. So when there is a problem in the cell, the proteins, there is not enough proteins or not enough amino acids, the cell stops working or minimizes working, but wants to preserve the ribosomes. And they are preserved this way for better times. So this is also very clever. So a few words about how did we work. I already related to it, that I myself doubted that it's possible, and this is because many others did. So at that time, the only way, at that time, and I'm talking about 1980 exactly, or last 2 weeks of 79. The only way to determine structure was crystallography. This needs crystals. You look at the diffraction of them with X-rays. So we bomb them with X-ray. The X-ray are diffracted. And the diffraction is done according to a mathematical rule, which is called transform Fourier. We can collect it all. You see here the crystallographer, this little person here, is collecting all the data. And because we know that it's done by transform Fourier, we operate on it by opposite transform Fourier. I will remember the word in a minute. And we can get the structure. For this, we need crystals. So what are crystals? Let's look at the salt crystal, sodium chloride, that like spontaneously to make periodic structure, periodic packing in 3 dimensions. And this is wonderful for salt, and it's done spontaneous. When we buy salt, we get a little bit of shiny pieces. These are the crystals. So it's okay for anorganic materials. Also, proteins were crystallized already in the 60s. In the beginning in Oxford and Cambridge. Cambridge did hemoglobin, myoglobin, and in Oxford they had lysozyme. And a 6-year grader, less than 12 years old, could repeat it. So proteins can be crystallized. By these ones, now that we know the structure, ribosomes, can you think about having all of them standing in line periodically in 3 dimensions. This was a big question mark, which actually say it's not possible, since very established scientists with very established labs before me failed. And they explained their failure by, they explained why the ribosomes were considered not crystallizable because they didn't crystallize. They explained it by high degree of internal mobility and flexibility and a lot of heterogeneity and chemical complexity. And all of these are correct reasons why ribosomes didn't want to crystallize. But in my opinion, they didn't give enough importance to the marked tendency, to the instability. Why did I think about this being the main reason? Because when I made ribosomes myself and I repeated procedures in the literature, I didn't have none of my procedure, but I used what was published. I always got less than half activity of what I was expecting, according to the weight of the ribosomes, the number or whatever you want to call it. And I thought that I'm not a good scientist. I don't know to make ribosomes. But I contacted the laboratories that published the procedures, and I told them, and they said, no, nothing. It happens to us too. It's always like this. We never get full activity, less than half, maybe third. So then I thought, if one has in the test tube full ribosomes and some deteriorated ribosomes, how can you expect crystals? The heterogeneity of your system is already done. So this is what I thought, and then I had a big accident, and while I was brain concussion, and when I was recovering, I read all types of things, all types of reports, and I read about a report of a delegation that went to the North Pole to see how the bears are existing while they are asleep during the winter. So they found all types of things, and one of them was that the ribosomes are orderly packed in the inner side of their cell membranes. It means within the cell. So I thought, here, nature can orderly pack ribosomes. They can be packed. People couldn't make it. People couldn't even have monolayer. And every bear, every winter, every cell must be a mechanism. And I thought, why is this mechanism? I thought that when bears get up at the end of the winter, they need to function, and then they need proteins. And for making proteins, they need ribosomes. And if they won't pack the ribosomes, they will lose them, because ribosomes don't stay so long, because they, as I told you, they are deteriorating fast. So I thought this is the way to maintain activity for stress problems. It means stress induces periodic packing of ribosomal particles. But stress is not only cold weather, it can be also hot weather, it can be just bad conditions. So my solution was to use ribosomes from bacteria that live under extreme conditions, like hot springs, waste of nucleic facilities, and the Dead Sea. The Dead Sea is the lowest part in the world. It's very, very salty. It's in Israel. You can see all these are salts coming out here. Salt coming out when it evaporates during the summer. The temperatures can get up to 50. So it's very, very salty, very full of halogens, and very, very hot. These are extreme conditions. And it's called the Dead Sea because there is no animal there, no flower, no tree, nothing, just salt, salt, salt. Yet there are two types of bacteria. You can see here bacteria. You can see here bacteria, these pink ones. And I knew about this bacteria. It's called Heloarcula marismorti. Marismorti is Dead Sea, I think you know it. I worked on it earlier, so I knew about this bacteria. We extracted its ribosomes, and we got crystals. We also looked at bacteria that live in sewage of nuclear facilities, because this bacteria, it's called Deinococcus radiodurans. It's made, each of these is a cell of 4 rooms. One room is functioning, and when it is destroyed by the whatever, it can be the radiation. The second one is coming into power, and the other 2 are repairing. So we worked on this also. This is a very, very stable bacteria and environment, dust, radiation, everything. And we got crystals. In the beginning, we got small ones. This was the middle of 1980, you see. Very much in the beginning, 29, experiment 29. And these were not good for crystallography, but you could show that there is a structure, a packed periodic structure. And at the end, we got many, many types. I don't want to show you all of them, but I don't want to talk about all of them, but please have a look how beautiful they are and how well ordered they are. Then we could go to synchrotrons to measure. So the synchrotron in Brazil is in Campinas. I visited there, but I didn't work there. I did work in several others in the United States, Chicago, Cornell, in Japan, in Germany, where I actually really had a group. And this is the one in Grenoble. It's so beautiful from top, I decided to show it. We used it a lot. And you can see from top, really beautiful rivers, green, snow on the mountains. And when you get closer, it's less beautiful, but it's not so important. What's important is how it works. So the particles are being accelerated and then running in this circle. And in the tangential beams are coming out. And each of them is a station and can be used. Like here, we are using it for ribosome structure. So in 1986, we got beautiful. First time we got beautiful diffraction. The diffraction is in the reciprocal space, so the further from the center, the higher the resolution. And this reached the border of the detector. Just fantastic. And we were so happy, the student jumped up, we got it, yes. Not for long. Second one was already deteriorated. Just this. So we repeated this experiment 100 times and in 6 different facilities. And always we got maximum 2 pictures, which was less than 1% of the data that we needed, because we needed the whole circle. So at that time, I thought this is the time to stop. Or how did we describe it? We described it that crystallizing ribosomes was considered climbing the Everest, and we came from this side and we saw only this mountain, and we climbed it and climbed it and climbed it and climbed it until we got to the summit. And then what did we see? That there is a bigger Everest behind, and we have to climb this one too. And this I was not sure we can. And how? Because the crystals are decaying. So I don't want to tell all the story, but the crystals were readily damaged, and we found a way to preserve them by understanding that the damage, instead of stopping the work, I tried to understand. And I understood that there is a primary disruption of the beam. The beam breaks the bonds between the atoms. And then each atom is not happy after the bonds was made, so they are propagating. They are running around to either to give the extra electrons or to look for missing electrons, and they're breaking more and more bonds. So I understood that we cannot change the primary problem, that the disruption of the bonds. That this was less important for us as long as the atoms stayed in place. This, I thought, the propagation, the running around, we can minimize by working in very, very low temperatures, by cooling down the crystals while collecting the data, only then to minus 200, minus 195. So everybody said it won't work, and here is the experiment. We collaborated with Hakon Hope, who died a few months ago. This was done in Stanford. You can see in my face that even I didn't believe much in it. And everybody was laughing at us, like this professor that came to visit. They laughed, but it worked. Look how wonderful. And you saw the structure already. And you can see me 20 years later in Grenoble in the synchrotron. Each synchrotron now has this cooling, and the liquid nitrogen is coming just on the crystal that's here. You can see it. You can see a picture of it from here. And we can collect almost full data from one crystal. They hardly decay. Not only us. Within a few months, we did it in November 86. In the beginning of 1987, there were only about 100 structures. This is the name of the structures in the whole world. In 2011, we're already 57,000 crystal structures, almost all, 99% collected under our suggestion in cryotemperature. And now there are 100, now in 2020, there are 105,000 structures, all collected this way. And it became a whole revolution, because most of the compounds, compounds that the structures were made were of very important new materials or new pharmaceutical materials, and a lot of proteins and assemblies of proteins. So even the Nobel Prize announced that the prize is given for the structure of ribosomes and also for the cooling, for the cryocrystallography. So during the whole study, 20 years, not the whole, 15 years, I was the joke of the world. Everybody said that I'm dreaming, I don't understand what I'm doing, and so on. Not everybody must, but most. After about 15 years, when we showed, after making the cooling and better crystals and so on, we showed that it's possible, and then we had lots of followers. 2 of them got the Nobel Prize together with me, although we were 3 competitors. But what I want to show here, and this is not my creation, it's Vlodaware that made this picture, is that there were 2 schools of biological crystallography. One in Britain, started with Bernal, and one in the States, it is Louis Pauling. And they came out with many Nobels. Each of them is a Nobel of somebody else. And some that don't have Nobel but deserve it. Look how many, just for protein structure. But where am I? I was not in Britain, not in America. I'm here. You see here, which is called treeless. So that's more or less the end of my story. Just to tell you that we found that all the ribosomes have the same structure where the peptide bond is being made. It didn't change with evolution from the smallest bacteria to the biggest elephant. So we thought that it's not evolved. It means it can be the most ancient part. Maybe it's prebiotic. So we decided to see whether just this part of the ribosome, which is less than 4% of it, can function. We made in the lab, we created it in the lab. For about 10 years, we could create but not get any function. But recently, we already have 70 chains like this, and 5 or 6 of them could make peptide bond in the lab. It means maybe it was before life. So in this time, I want to thank the people that were important in my work. Professor Sela allowed me to work, although I was the joke of the world. Gandru, who determined the first structure of hemoglobin, he said that this is a project that shouldn't be stopped, although he was not really sure I can make it. So was Anfinsen that found out that structure is determined by the sequence. And Alex Rich, that tried to crystallize ribosomes for 10 years and could not, was also supporting. The most supportive was Professor Weizmann from Berlin, who had a whole big group of 245 people that all wanted to say all about ribosomes. So they could even have me as a guest in the beginning. But when the studies were more demanding, they started a group for me, a little institute in the synchrotron at Daisy. But Professor Weizmann was very important in doing, but he died 10 years before the structures came and was replaced by Franceschi and then by Fucini. So I had 2 groups, one in Hamburg and one in Israel. And I want to thank all the group members. I want to show you the group in Hamburg that was terminated in 2004, always had angels, but the assistants say that only angels can work on ribosomes. Here we all go to measure in Cornell. Here the way we measure, here the way the kids are. And this is the Dead Sea. The whole group came to the Dead Sea to look for better bacteria. I'm not sure they had better time. This is the group in Israel. Not all of them are still with us. Some of them left a few years ago. But I want to highlight Anat, Dr. Anat Bashan, who runs the group, and Ilana, who found a place where could be the beginning of protein biosynthesis, prebiotic, and Tamar. Tamar came 16 years ago, now it's 17 years ago, for 10 weeks. She's still there. And meanwhile, she came as a child for 10 weeks practicum, but stayed a long time. And here she had birthday and she baked a cake. Can you see the cake? Maybe you cannot. So here is her cake. And this shows that in my group, ribosomes are considered sweet. I also want to thank my family, my daughter and my granddaughter. She grew the first crystals. And they were always very supportive. My mother, my sister, I don't show all of them. And my granddaughter gave a speech when I got a prize in Paris. And she said about me, as you know, she is a very busy scientist, but she always finds time for us. And this was the most important thing for me. Actually, this is the Nobel Prize, but more important is what she said. The grandma of the year is Yonath, and she hanged it on the wall when she was, I think, 10 years old, which is 14 years ago. And I asked her, each prize has a year. What is the year here? And she said, the year, you have to reprove yourself every year. If you fail, I'll take it off the wall. So it's still there. And I want to show you that ribosomes became popular. Here, it's a carnival. He's me. And she is a ribosome. You see, they are dancing and protein comes out of her. And also young children became ribosomes. And I was shown by one of our best, most important artists and writer, head full of ribosomes. So if you look at it carefully, small subunit, large subunit, small subunit, large, small, small, And he thinks that new antibiotics should be here and here. Thank you.
Thank you. Thank you so much for wonderful and inspiring talk. We are so glad with your presentation at this very crazy and bad moment in our life. Thank you so much. Adriano,
Thank you for inviting me.
Thank you so much, Ada, for your wonderful and inspiring presentation. Wow, it's always a privilege to hear from you. And now we are going to open the discussion section. We already have a number of questions, and I encourage everyone to join our discussion. Please send your questions via the YouTube chat. First, I want to invite Professor Regina Marcos to make her comments and then ask the first question. Please, Regina, go ahead.
Ada, it's always a pleasure to meet you here and in Israel. The last time we met was when Mario Fleck got the Dr. Honoris Causa last year in Israel. And he's the president of the Amigos do Weizmann Brazil, the Friends of Weizmann Brazil. Yeah. And I am the vice president. So I came here honoring you.
Wonderful, thank you.
Not only as a scientist, but also as a woman and also as a mother and a grandmother. This is really something that it's always on fire. Mario, let a question regarding the possibilities of using basic science and pandemics as we have COVID. But I would like to make a question too, looking on ribosomes. So ribosomes, they are unique for each cell. So now, after all you have done, some people are showing that you have special ribosomes in each cell, in each kind of mammal cells. And you look at a lot on antibiotics, fantastic. I'm thinking on the virus, on this virus that is a retrovirus that is RNA. So it has to go inside, use the ribosome for himself, and that's it. Everybody is looking on the epithelial cells because there is the gate, AC2 is a gate, and everybody's looking in that context. But the virus, it comes to the body 4 to 8 days before it enters the epithelial cells. And there, in the middle of the air, we have special macrophages, the resident macrophages that came from the embryonic life with a chemistry that came from the embryonic life that are self-renewed in the lung, in the air portion of the lung. And I saw in my lab, because we are working with it, we can see that the virus can go inside the cells. So one thing that I want to propose you is that the difference in these cells, just one thing more, they used to be tolerant cells. They don't mount an inflammatory response, a proper inflammatory response. They receive the virus and they say, oh, guys, I will deal with this bad guy. You don't have to pay attention on it. So in many conditions, it will not trigger a huge inflammatory response. So my question, when I think why, I think that is because the virus that is formed in this special cell should be different and should not have all the proteins needed to invade the human cells. So might the ribosomes from resident macrophages be different from the ribosome from the ACE2 cells that are the epithelial cells that express ACE2? And then these first cells will translate and keep the virus and will not induce the disease. So it will be important to compare the structure of the epithelial macrophage with the epithelial ribosomes with the structure of the epithelial macrophages. Now I'm comparing two cells that should have different functions in the ribosomes. This is my provocation. It's not I don't have an answer, but it's a provocation, a scientific provocation. And resident macrophages are my guys at the moment.
You're right, and it's really interesting. I think that there is some literature about. I don't know it, but I think that there is some literature about the differences in ribosomes. We know that ribosomes grew larger with evolution, and the minimum was this pocket that I showed it at the end of the lecture. But we don't look at it. Maybe it's a good idea to do it. What we do now, and I didn't tell about it at all, there are diseases in which part of the ribosomal proteins are mutated. And we are looking at these diseases. There are anemia, there are many cancers.
Yeah, I saw it in cancer.
We are looking at them now. We are trying to understand what happened there.
So my suggestion is to look between healthy and healthy two kinds of cells.
Yeah, but what I wanted to say is something that I admire the virus. It goes into the host cell and takes its ribosome, uses its ribosome for its own need for proteins and for its growth. Really clever.
Yeah, it is clever.
And I don't know how it does it.
But I think that macrophages should be clever. The ribosomes should have differences. And the difference in ribosomes should give protection.
Could be, yeah, it could be.
And this could be another door for understanding virus, not COVID, but virus.
You're right.
Thank you very much.
Thank you.
Okay. Thank you, Regina and Ada. Now we will go ahead and take some time for questions from the audience. We have here a question from Toshifumi Kawakami. What are the major difficulties for the development of a vaccine or drug for COVID-19? Ada, please.
It's not what I'm doing, but
it's your general opinion, yeah.
In terms of vaccine, there are several ways to do it, and there are already two attempts that two companies that say that they are doing it. One is Japanese, Keade, and one is American. There are also two universities. There are also studies at the Weizmann Institute, where I am. But there are difficulties because we don't know exactly to which part of the virus this vaccination should bind. What is the best position to stop? The structures of all the components are not all of them are known, and we have to remember there are previous viruses from the same family, SARS and MERS, and people thought that it's possible to use the vaccination for them. The vaccinations are not so good even for them. And so far, it wasn't shown that it can be good vaccination for COVID-19.
Okay, good. The next question is from Leonardo Ferreira. How do you see the evolution, advantages, and limitations of cryo-electron microscopy and structural biology?
How do I see? Fantastic. Now we can see everything. First structure took us 20 years. Well, we had two structures in 20 years. And two people that copied from us, each of them worked about 5 or 6 years. Now we get structures in months if the preparation is good and if the microscope is good. So these are ribosomes. They are very large, but not the largest. And people look now at fantastic assembly. I see the future being fantastic.
Yeah, very good. Now a question from Luisa Coutinho. Do you have any advice for young scientists that are still in college or grad school?
Yeah, I have one advice. You want just one? You want to hear? Yes?
Yeah.
Don't look for advices.
Why not?
Do what you think is right. What is advice? Somebody copies me, I copy somebody else. Everybody is different. The knowledge is different. The wishes are different. The education is different. The environment is different. Do what is really interesting for you and you love to do it. Don't look
Very
for
good.
it.
This is a great advice, in my opinion. Okay, now, Paulo, now I want to hear your comments and your question to Ada. Please go ahead.
Ada, a comment and a question. The first, I found beautiful the end of your presentation where you put clearly the conflict that all scientists have to do with the timing dedicated to hard science, that's very hard in general, and family and friends and and the life together with human beings. I think that was very beautiful, very nice, and I think it's a lesson that all of us have to do. My question to you is the following. You discussed on your presentation, that was very comprehensive, the critical issue of antibiotic resistance. And also you mentioned that the big pharma, the big laboratories are not searching anymore for new antibiotics, and this will have a tremendous socioeconomic impact in the very near future. Question to you, why the governments, let's say Israel, Brazil, UK, US, does not enter and started, seriously as an international initiative looking for new antibiotics?
Okay, it's not looking for, it's designing. And
designing.
And new ideas, like our idea that we have these positions that we already put things on them, but no company, not pharma company want to take it. So the governments understood it. About 6-7 years ago, they started, and about 3 or 4 years ago, there were moves towards research on antibiotics. So the European community, the ERC, the G20, the G7, and of course America and Japan, they all said they are going to provide money for research on antibiotics. And they do. And they even took one of our pictures for their, the ERC, for their propaganda. But governments cannot make anything. They can support science, they can support research, but the companies, they cannot work on the companies. What will a government say to a company? The company needs investors. If governments would invest as much as investors, it would be different. But so far, governments understood it, but they could not force the production. They could help the investigations, the science.
Oh, okay.
And they do this.
Mm-hmm.
There are some grants for that.
Okay, thank you. Now we will take the last questions from the audience. We have a question from Felipe Bagatelli. What will be the next breakthrough and challenges in the ribosome field?
So I don't know. I'm not a predictor. and I know that there are many surprises. But as I mentioned earlier, there are ribosome diseases. a very important question is how the viruses force the ribosome to work for them. If they sneak into the line or influence the line. And in my opinion, the evolution, it means the origin of life. If it was really what we think, the prebiotic piece that is still embedded in the ribosomes, if you understand this would be a breakthrough, in my opinion, at least.
Okay, very good. Now a last question from Marilia Valli. Why resistance could be minimized by developing species-specific antibiotics?
Okay, I understand the question. All the antibiotics that are now in use are for all bacteria, right, including the good ones. So if one has a problem that only one type of bacteria is involved, which is usually the case, but when giving I don't want to say all the antibiotics, but most, when giving a larger collection of antibiotics, more resistance will happen, even if 90% of these types are not needed. So if it's specific and it can be found which bacteria is there, and there are specific, it will, if it's bad or good, at least it will have influence only on one. Now the question is, what happens when a person comes to a hospital with high temperature and something that looks like infection? So first of all, his life has to be, or her life has to be looked at, have to be rescued. So that the doctors give all the possible antibiotics, the biggest, the widest collection. And then I think this will be done even in the future. But then the samples can be taken from the ill person, and the actual bacteria can be determined, can be isolated and identified. Now it takes a long time. Most of the hospitals and most of the, I don't want to say most, but whatever I know, many hospitals have the possibility to do it, but it takes a day or two. That's much too long for infection. However, there are companies and already machinery that is being sold, tabletop, very small, for 6 hours, identification of which bacteria. And these facilities are being checked. Now some are better and worse. I don't know much about it. But if this works, then they can say, oh, this is bacteria Staphylococcus. So let's take the antibiotic for this bacteria. This is why it's much better. And not a whole range of bacteria, which may be good ones and some are not needed and so on.
Okay, thank you. Vanderlan, now the floor is yours for comments and your question. Please go ahead.
I'm not sure if I have questions. Maybe taking account all studies you have been dedicated to ribosomes, and also the problem of antibiotics that Paulo Artacho mentioned. What structure of antibiotic you have been working until now you think that could be invested for COVID-19? Because you have...
COVID-19 doesn't need antibiotics, it's a virus.
Yeah. Okay.
Antibiotics are working on biotics.
Okay, okay.
For COVID-19, there are some attempts to stop where it works. It means like a medicine, and also vaccination. In my opinion, the way to get rid of COVID-19 is vaccination.
Mm-hmm.
Okay,
Yeah.
thank you.
It's
Thank
cleverer than us.
It looks like we have covered all the possible questions. Now I would like to hand over to Regina, Paulo, and Vanderlan for the final, very quick comments before the wrap up. Please, Regina, go ahead.
Vanderlan, Adriano, Paulo, congratulations for this initiative. I think that ACIESP is really on top with this first meeting and being Ada Yonath that represent science, women, and free thinking. Ada, you for me is someone that comes from Jerusalem, that comes from a background full of learning, full of liberty of study. And you use this to jump to science in the same eager way that everybody studies philosophy, and we learn how to study. And this liberty of studying is translating in the way that you are presented to us today. And I know that you like Brazil very much, that you came to Brazil many times. And really, Brazil is a land, a special land. It's a land that received all our families here with every time opened. And here we have people from many sides of the world. We can say we have problems, but not so many. And ribosomes, crystallize, goes on a very, very deep understanding of a problem, is basic for jumping to new eras. So nobody will get new antibiotics, nobody will get new understanding of virus if we stay doing the same thing that everybody is doing. And we, for me, is an example of someone that jumped, missed the word, jumped the fence. Is this the word that I want to say? I don't know if it's so nice in English as in Portuguese. So you go behind, is as Alice in the wonderful word. So Alice, Ada, Yonath, Yonath, peace. Thank you very much for being here today in this morning. It was really amazing. And Vanderlan, thank you for the opportunity.
Thank you.
Paulo? Microphone, please.
Microphone.
Sorry. I think one thing nobody mentioned, that you is a beautiful example on how basic science, because nobody was even mentioned it, that 20 years ago, the use of X-rays could bring this revolution in the study of life. So it was really beautiful to see how basic, it was a living demonstration that basic science is essential for humanity. Let's not just look for applied science, of course, is also important, but the fundamental things that you teach us on this lecture were very, very nice and important for new scientists, students that are seeing this webinar. So basically, thank you very much for your beautiful lecture on science and also on life.
Thank you.
Okay. Thank you. Vanderlan, please.
Okay. Thank you so much, Ada. I am a little emotion with this. You accept our invitation. And also I agree with Paulo Artacho. You showed to us the importance of basic science as for the knowledge of a development of humanity. It's very important nowadays in our country. I think in all over the world, but in Brazil, that's developing country, and you need to have inspirations for new generation, even so for old generation. You are inspiration for us, and your talking today was wonderful as ever. Thank you so much to stay with us in these first webinars of our Academy of Science. Thank you so much.
Thank you.
Ada, please, your final thoughts.
I had only one final. Thank you.
Okay, very good. Time's up.
I'm really happy for meeting with all of you, and for at least mentally being in Brazil. And I wish you the best, and I hope you get out of this corona fast and without so many casualties. It's important for me to know this. So good luck. And
Thank
good
you
luck
so
with science.
much. Thank you so much for being here with us. Let's close this webinar. We hope to see you again next time.
Adriano, I would like, sorry, just a minute, to thankful to Luis Melo and FAPESP for great support today to have this wonderful talking with Professor Ada Yonath. Thank you.
Thank you.
Okay, yes. And also thank to Marcelo Meletti, Roberta, and Felipe from FAPESP, and to my assistants and colleagues here today, Marília, Leonardo, Alex, and Pedro. And finally, thank you all for attending and have a great day.
Thank you.
Thank you.